Start recording. Okay, we were talking about the machining last time. We stopped here about the chip morphology. Chip is a part of material being removed from the machining. Whenever we do cutting, whenever we do machining, the part of material being removed, we call it chip. This chip is very important actually because a chip here is dependent. If you remember, a chip is dependent parameter, dependent on what? Dependent on the cutting condition, dependent on the power being used, dependent on the whatever you input in the machining, what tool being used, geometry of the tool, what is the workpiece material, what is the cutting condition you use. So chip is really important, and the morphology of a chip tell us many information about the cutting. So analysis or analyzing chip usually tell us many information about the cutting. Generally, in a chip here, you can see this is a tool, this is a workpiece, this is a chip. As I told you, part of material being removed. Here, this area we call it is the primary shear zone. This area we call it secondary shear zone. Primary shear zone where material be sheared here. As you can see here, material here, the tool here shearing the material in the shear plane. This one we call it primary shear zone. Here also there are a shearing here because the chip is moving. Chip is moving, as you can see here, chip moving in this direction. While chip moving in this direction, you can see here in this area, high friction between tool and chip and leading also to another shear, we call it secondary shear zone. So primary shear zone and second shear zone. This is generally, when you come to the chip details, you can find that this photo or those photo telling us different story about different chip style for different machining. This one we call it is a continuous chip. This one we call it continuous chip, is continuous chip with a narrow straight primary shear zone. This is a shear zone, primary shear zone, narrow straight primary shear zone. Okay, this one is a secondary chip here. If you magnify this area, you can see this is a secondary shear zone in a tool chip interface. Another story here in this photo, you can see that another story here in this photo, you can see that this one we call it is a continuous chip, like this one, continuous chip, but with built-up edge. This is a built-up edge. We have here whatever we call built-up edge. We will discuss what is the details or what is a built-up edge, why it happened, good or bad, and so on. We're going to discuss the details. So here with the built-up edge, here we can see that this is also continuous chip with a large primary shear zone. This is a shear zone, big shear zone. We will discuss why we have large primary shear zone. This one we call it segmented, and this one discontinuous. Segmented and discontinuous. You can see the difference here. This continuous, this continuous, this is discontinuous. You can see the part of a chip is separated. As I told you, every case have a certain reason why chip is coming like this. So whenever you get a chip, actually, we can realize what is that, what is a cutting, what happened in the cutting. The details of cutting can be understood, or could be understood, or we can understand what happening in a cutting from the shape morphology, right? That's why chip morphology is very important. Okay, continuous chip. Start first with the continuous chip. Continuous chip actually, as you can see here, this is the cutting. This one is a continuous chip. Is a narrow shear zone. Is also secondary. Here is the primary shear zone. Here is the secondary shear zone. This is a narrow straight. The continuous chip. Excellent finishing happen. Usually, this one coming with ductile material. This one happen in cutting ductile material. When you cut ductile material, usually continuous chip occur at high cutting speed and high rec angle. High cutting speed and high rec angle, as you can see, and may occur also at low speed and low rec angle. But in case of you cut soft material, very soft material, in cutting soft material, then characterized by wider shear zone. So wider shear zone here happen in this case if you have a low cutting speed and low arc angle and you're cutting soft material. It happen also. Then continuous chip happening for both cases. High cutting speed you get a narrow and straight and narrow, but if you have low cutting speed and low arc feed, but cutting also soft material, then you get continuous chip also, but with wider shear zone. Then shear zone usually or primary shear wide, and you get a bigger chip thickness as you can see, right? This is a continuous chip, and this is a photo of continuous chip is coming. Can you see that this is a very long continuous chip coming from the cutting, different type of continuous chip coming from cutting, right? Next is build-up edge, continuous chip with a build-up edge. This is a part of the build-up edge. The build-up edge actually is a part of a chip is a stick with a tool. This is a tool. Can you see that? This is a tool. While cutting part of a chip is stick with the tool. Stick with the tool mean instantaneously adheres to the tool. يعني stick with the tool and become secondary edge of the tool, part of the tool. Later it will be separated. Later it will be separated. Another part comes stick with the tool and so on. When you look to here, you can see that this is a build-up edge. We know the build-up edge for the tool. This is a tool edge. Then you see that some part of a chip here stick with the edge of the tool. So we can realize that this is the build-up edge. Why build-up edge happen? Is it good or bad? Actually, it is bad. Whenever you have build-up edge, it destroys the workpiece. Can you see that? Workpiece quality is getting very bad. Either, even this build-up edge improving the tool condition. Because built-up edge stick with the tool is like you added material to the tool and working like another edge of the tool. Then this probably increase the long life, increase the service life of the tool, but in some cases increase the service life of the tool, but it damage the workpiece. This is really deteriorating the workpiece surface, and we should avoid having this kind of build-up edge. It happens whenever we have chemical affinity similarity between the tool and workpiece. Then big atomic aggregation happen, and then instantaneous adhesion or instantaneous weld happen between part of chip and tool, leading to this phenomena. Also, it happen when you're cutting material at very low speed. When you're cutting material at low speed and low depths of cut, low speed and high depths of cut. It happen when you're cutting material at low speed, high depths of cut, high feed rate. Because when you're cutting at high feed rate and high depths of cut, big amount of material is coming and low speed, then speed will not be high enough to remove this kind of material. Then pressure will be very high. This one also leading, and temperature also increase. This one leading to the build-up edge. Actually, as I told you, this one totally damaging the surface of the workpiece here is not good really. This is bad. We can improve the situation by two cases using cutting fluid, whatever oily type cutting fluid. Cutting fluid means the liquid that we use in the fluid. When you use a cutting fluid usually prevent this one from happening. This is one. Another also, we can increase the speed, cutting speed, increase the cutting speed, and also using cutting fluid to prevent build-up edge from formation, prevent the formation of the build-up edge. Next is a discontinuous chip. This is a discontinuous chip is mainly with a brittle material, mainly with a brittle material. Discontinuous chip is mainly with brittle material. We're cutting brittle material, or we have inclusion material, have some inclusion, foreign material, and so on. Then you can see discontinuous chip happen. So this is a discontinuous. This is a photo of this. It is not continuous, discontinuous. So part of chip is being removed, as you can see. It happened at low speed, it happened at high speed, but when you're cutting brittle material, this is very common because of the discontinuity nature of the chip. Because of here, you can see that discontinuity. Because of the discontinuity nature of the chip, as you can see here, Force vary continuously, leading to vibration in the machining, a chatter in a machine tool, with end result of the poor surface finish, and tolerance is also bad compared with other cases. So cutting fluid help actually. Cutting fluid help to improve the situation. So we usually also in case of this kind of machining or cutting fluid should be provided or assisting this machining. The next one is serrated chip. Serrated chip very similar to discontinuous, but it is another story because here it happened because of cutting material that have low thermal conductivity. Low thermal conductivity material accumulate temperature. Low thermal conductivity, it means that when heat created here, material not dissipating heat easily, then material accumulate the temperature in the cutting zone, then temperature in the cutting zone increase, highly increase here. Then what happening here? Then hardness of the material or strength of the material drop significantly because temperature increase. Then the strength of the material drop significantly when cutting happen, like cutting of titanium, as an example, cutting of titanium, and this one leading to strength drop significantly, leading to separation. As you can see, we call it serrated. This material is not brittle, but the problem is it is low thermal conductivity material, and this one finally leading to, as you can see here, whatever we call serrated chip, as you can see. Right. This is a chip morphology. So based on that, if you have any type of this chip, we can understand what is the story behind the chip, I mean machining story behind our chip. Next, we're going to talk about force analysis of orthogonal cutting. Force analysis of orthogonal cutting. This is really important to properly design a machine tool for a vibration, a chatter-free vibration, and so on, to understand how material strengths affect the cutting force, how material strengths affecting cutting force, how this cutting force is generated, so we can plan for cutting to determine horsepower, what is the power needed, so we can obtain or we can assign the suitable machine for machining or for cutting and so on. Okay, in a cutting, this is a cutting, this is a tool, this is a workpiece, this is a chip, right? This is a tool, this is a workpiece, this is a chip, this is a shear plane, this is a shear plane, right? So the tool shearing the workpiece here in a shear plane, right? Exactly. When cutting happen, listen to me carefully, please. Please listen to me carefully. Please give me your attention. This is really very important. When cutting happens, six components of cutting is generated. Two color, as you can see, two in the red color, two in green color, and two in black color. The two in red color, FC and FT, cutting force. This is a tool generating cutting force, cutting force. This is a thrust force. So 90-degree between. This is the FT is the thrust force. FT is the thrust force. So FC cutting force, FT is the thrust force. Another two forces generated is F in black here. This is the friction force. Friction here because the chip is moving, right? Chip is moving in this direction. Let me show. Chip is moving in this direction. And actually, very high friction happen in the shearing zone. Very high friction happen here as in the cutting zone here, in the secondary shear zone. So this is a friction in the same direction, friction in the same direction of the tool edge. So this is the friction force. This is n normal to the friction force. This is the friction force. This is a normal to friction force. The angle is 90-degree. This is the R resultant force, and the resultant force is same for FC, FT, F and N, and also another two forces is FS. FS is in the shear plane, generated in the shear plane, and this force it happened to shearing the chip, to shearing the workpiece material. Then Fs and Fn normal to the shear. So Fs shear force, Fn normal to the shear, and R is the resultant for all. If you draw circle, the circle will pass through all these forces. We call it is a merchant circle. So this what we call is the merchant force circle. This circle we call it is a merchant force circle, right? Angles here you can see, if you have a vertical line here, this angle is alpha. So this angle is alpha. You can see this is alpha, this is alpha. So this is a vertical line with a tool, alpha, this is alpha, right? Okay, this is the angle here, this angle, we call it beta. This beta is a friction angle. This beta is, we call it is a friction angle. And then tan beta equal to F divided by N, which is mu, friction angle. Beta is a friction angle, and tan beta equal to for Fn, F equal to mu N. Generally, friction force equal to mu N. Then F divided by N equal to mu, or mu equal to F divided by N, which is the tan beta. So tan beta equal to F divided by N. This angle is alpha. This angle is also alpha with the horizontal line is also alpha. And this angle here, this angle is equal to beta minus alpha. This angle is beta minus alpha. This angle is beta minus alpha. This angle is beta minus alpha. This angle, sorry, this angle is beta minus alpha. Then this angle is beta minus alpha. So this is the angle in the merchant circle. You must know, you must learn how to draw the merchant circle. You must learn how to draw the merchant circle. So let me show you this one. Let's practice together. Let's practice together how to draw the merchant. Right. This is a tool. Please give me your attention. This is a tool. So this is a tool, right? In a tool, we have 6 components of the force. I'm now trying to practice with you how to do. You must do by able to do by self. So give me your attention here. This is really very important. This is the cutting force, Fc. This is the normal to the cutting force, Ft. This is the two component, and this is the resultant. Resultant is R, right? Another one, you see that here, this is the tool edge. This is a tool, right? This is a tool. This is a tool. This is the tool edge. A friction force in the same direction. Friction force in the same direction. This is a friction. This is a friction force, right? This is a normal to friction. And this is also R. Another two component is a friction, is a shear. This is a shear force in a shear plane direction. And this is the normal to the Fs. Right, let me write. Then this is FC cutting force. This is Ft thrust force. You must know how to practice. This is the F friction force. This is the N normal force. This is the Fs. This is the Fn. This is the R. R is the resultant. R is the resultant. This is the 6 forces you have to obtain. Whenever you come to the angle, this is really very important. Whenever you make a vertical line here, this is a vertical line here, and this is definitely extended the vertical line like this. Then this angle is alpha. This is the tool angle, right? This is alpha. tool angle with, then this is the angle is alpha also. So this is alpha. Alpha here is a tool angle or rake angle. This is alpha, right? Okay. You give me attention, please, guys. This is really very important. This is phi. This angle is phi. This angle is phi. Phi is this is a shear plane. This is the shear plane, and this is phi shear plane angle, right? This is a shear plane angle. This is a shear plane. This is a phi. This is a beta. This angle is beta. This angle is beta. Beta is a friction angle. We call it is a friction angle. Beta is a friction angle. Tan beta. Let me write tan beta. Tan beta. Tan beta equal to F divided by uh, divided by N. Then tan beta equal to F divided by N. Tan beta equal to F divided by N equal to what? Equal to mu. Equal to mu. Mu is a coefficient of friction. So mu equal to F divided by N or tan beta. If you make this angle, if you make horizontal line here, then this angle will be alpha. Then this angle, the balance remaining is beta minus alpha. Then if this one beta minus alpha, then this one also beta minus alpha. So this one here is also beta minus alpha. Sorry for writing is difficult here. So this is how to draw the Merchant circle. This is really, 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 really very, 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 very much important. You must practice by yourself. You must learn how to draw the Merchant circle. You must practice by yourself. This is very easy. This is very easy, as you can see here. Okay, any question? Guys, any question? Is it clear? Is it clear how to practice? How to draw the Merchant circle? Okay, get back to the slide again. Then an immersion circle here, you can see that this is a tool, this is a tool, then this is the FC, this is the FT, this is the FS, this is the FN, this is the F, this is N, this is alpha, this is alpha, this is beta, this is beta minus alpha, this is beta minus alpha, this is phi. Phi is missing here. Let me just have this is here, this one is phi. So phi is missing here. So this is phi. Where phi here, this is phi, huh? This is phi. Phi is the shear plane angle. So this is a Merchant circle. Among all these six forces, FC and FT, only FC and FT can be measured experimentally. FC and FT, only these two forces can be measured experimentally. Experimentally, how to measure experimentally FC and FT? We use whatever we call dynamometer. There are whatever we call dynamometer. It is device. We use this device to measure the cutting force. And this device we put in a table, as you can see, and we do cutting. Then by using this device, we can measure only FC and FT. FS, FN, and F and N we cannot measure. We cannot measure experimentally. So the question is how to obtain FC and FT we can measure. What about the other four forces? Actually, we can obtain the other four forces as function of known. So unknown forces can be obtained as a function of known forces. So Next, we would like to make a relation, to get a relation between the unknown and known. So we can use this kind of relation to obtain the unknown forces as a function of the known forces that can be measured by the dynamometer. Right. Uh, First, we need to obtain the relation between F and N, Fn with the Fc and Ft. So actually, let me tell you, this is the Fc, this is the Ft. This is the F friction and normal to friction. We need to get a relation between Fn and Fc and Ft. Uh, they extend this green line. They extend this green line to help to get a relation between, as I told you, right? Then you can see that OA, please give me your attention, OA as a vector equal to CB, equal to CB, then CB equal to CG plus GB. It is written here. This one is written here. You can follow here. So it is equal to CG plus GB. This GB, this line can be obtained as FT, this is alpha, this is alpha, this is beta minus alpha, this is alpha, then can be obtained as FT cosine alpha. This GB equal to FT cosine alpha in this triangle. And CG, this one equal to DE in this triangle, can you see that? DE equal to this DE equal to this is alpha, then equal to this line which is FC sine alpha, FC sine alpha. So this is FC sine alpha, FT cosine alpha. And also same, if you talk about N, this is N. I would like to obtain N as a function of FC and FT. Then N equal to OC equal to OD minus DC. Then OD in this triangle equal to FC cosine alpha, FC cosine alpha. Right, FC cosine alpha. Then this is the OD minus DC. DC equal to this line FEG, which is in this triangle equal to FT sine alpha, then minus FT sine alpha. This is the OD minus DC minus this area. This line is equal to FT sine alpha. This is the two relation. Then equal to F equal to F, which is the friction force, unknown friction force, equal to Fc sine alpha plus Ft cosine alpha. Then Fc and Ft, then F obtained as a function of known Fc and known Ft, and also angle alpha, which is the rake angle, which is the tool angle. We can actually measure. If you know the tool, we can measure alpha. And the N also, which is unknown N normal force, equal to Fc cosine alpha minus Ft sine alpha as a function also of known Fc and Ft. So unknown value can be obtained as a function of known value. The mu equal to F divided by N tan beta equal to F divided by N, which is the mu, coefficient of friction. Then F equal to mu N, then mu equal to tan beta F divided by N. Then you can apply, you can use this F and this N, you can apply here, then you can just get a relation as function of Ft and Fc. Then you can obtain the coefficient of friction in a cutting as a function of Ft and Fc, as you can see here. However, they say that if alpha equal to 0, it's kind of in in only this case, if alpha equal to 0, then you get this one, you get this case, because alpha is the angle, this is the angle, alpha is the tool angle. If the tool is vertical, and alpha equal to 0, as you can see here, what will happen? If alpha equal to 0, get this one is F equal to, this one equal to 1, this one equal to 0, then F equal to Ft, then F equal to Ft, this F will equal to Ft, and then N equal to Fc. Then F equal to Ft and N equal to Fc. because alpha equal to 0, because the sine 0 is 0, cosine 0 is 1. Cosine 0 is 1, sine 0 is 0, then n equal to fc, f equal to ft. And then means that you can use the dynamometer directly in case alpha, this is very special case, if alpha equal to 0, then f equal to ft. Then let me highlight, f will equal to ft and n will equal to fc. Then here you can use the dynamometer in case alpha equal to 0, you can use the dynamometer directly to measure the f and n, because in f equal to ft and n equal to fc, then you can use the dynamometer to measure. This is the only case, but generally we can use the dynamometer to measure fc and ft, and we can obtain f and n as a function of fc and ft as seen here in the two equations. Next is another two forces, which is Fs and Fn. We need to obtain Fs and Fn as a function of Fc and Ft as well. Okay, they also extend then Fs equal to OD. OD is equal to OA minus AD. Then OA, this line equal to Fc cosine phi. This is a phi. Phi is a shear plane angle. This Fc cosine phi minus AD. AD is equal to DBC, this line. This line equal to this line from this triangle equal to Ft cosine phi. Then Fc cosine phi, so Ft sine phi minus Ft sine phi. Fc cosine phi minus Ft sine phi. And also, this is Fs. Fn, this line, Fn, this line, can you see the green line, equal to DC plus CE. Okay, CE, this one, CE, from here to here in this triangle, equal to Ft cosine phi, and this DC equal to AB in this triangle, equal to Fc sine phi. So Fc sine phi plus Ft cosine phi. So this is another two equation. This is another two equation to obtain Fs and Fn as a function of Fc and Ft, and means that unknown force as a function of Fc and Ft that can be measured by the dynamometer. So this is the four equations. Now we have four equations to describe or to obtain unknown forces as a function of known forces. Right. Alternative ways. This is really important. This is really very important. I hope you give me your attention, because later this one help you to answer the numerical problem related to this kind of machining. So if you don't understand, it will be difficult. So understanding this one is really very important. So please give me your attention. Alternative way. What is the alternative? يعني الطريقة البديلة. حل تاني. احنا الهدف ان احنا عايزين نجيب ايه يا شباب؟ عايزين نجيب ال unknown forces as a function of known. Okay, let me tell you again. This is the Fc, this is the Ft, this is the Fs and Fn, this is the force F, direction force, and this is the normal, and those are the angles, right? Listen to me, guys, listen to me. Start one by one. Fc, what is the relation between, then you obtain all forces as a function of R. As a function of R. Can you see that? As a function of R. All forces as a function of R. Then Fc equal to what? Equal to R cosine beta minus alpha. R cosine beta. How is this beta minus alpha? We described that earlier. We're practicing how to write or to draw the Merchant circle and angles. You must be able. I will not show you the Merchant circle anymore. You must know what, or you can just draft the Merchant circle in a paper and must know how to do it. This is, you must practice how to do it. Anyway, then Fc equal to R cosine beta minus alpha. Okay, Ft equal to R sine beta minus alpha. Sine beta minus alpha. Okay, R sine beta. Fs equal to what? Fs, guys, Fs equal to r, this is right angle. This is right angle. Let me show you. This is right angle. This is the right angle. Okay, this is right angle. Don't forget that. This is the right angle. Okay, Fs equal to what? Fx equal to r cosine this angle, phi plus beta minus alpha. Then Fs equal to r cosine phi plus beta minus alpha. Okay, Fn equal to what? Fn equal to r sine phi plus beta minus alpha. This is the angle. Then Fn equal to r sine phi plus beta minus alpha. F equal to what? F here. Friction force F equal to R what? Sine beta. Then R sine beta. N equal to what? N equal to R cosine beta. R cosine beta. This is the sixth equation. This is the sixth. From where? From the Mercian circle. Then from the Mercian circle, we obtain sixth equation. If you would like to obtain, for example, Ft as a function of Fc, you see that what to do? Simply you divide here. You divide here. Right? You divide here. Whenever you divide, what will happen? R go with the R. Right? R go with the R. Then Ft equal to what? Fc equal to what? Fc equal to, this is Ft cosine beta minus alpha divided by sine beta minus alpha. This is Fc and Ft. Okay, this is Fc. So now if I would like to get the relation between Fc and Fs, okay, same Fc and Fs, then you R go with the R. Then Fc equal to what? Fc equal to Fs cosine beta minus alpha divided by cosine phi plus beta minus alpha. Then Fc equal to Fs go, then Fs cosine beta minus alpha, Fs cosine beta minus alpha divided by cosine phi plus beta minus alpha. Any two relation. What you would like to have, you know Fc, you would like to get Fs. Then bring the equation of Fc and the equation of Fs. You divide together. R go with the R. Here R is same. This one go with this one. Then Fc equal to Fs cosine beta minus alpha divided by cosine phi plus beta minus alpha. Okay, Ft. I would like to get a relation between Ft and Fs. Ft and Fs. This is the Ft. This is the Ft. Let me just highlight it. This is the Ft. Okay, relation between Ft and between the Fs. This is the Fs. Ft and Fs. Okay, Ft and Fs. Divide. You divide Ft and Fs. R goes R. Then Fs go here. Then Ft equal to Fs sine beta minus alpha divided by cosine phi plus beta minus alpha. Fs sine beta minus alpha. Then any two equation, you can use any two equation to obtain relation between any two force variable. Any question? This is really very important. This is really very important. Any question? Any question? Okay, so no question mean you understand. Please be sure to understand. If you don't understand, you can stop me anytime. Right. Here in a cutting, this is a chip. This is a chip. Let me show you. This is a chip, right? This is a tool. Tool now cutting. This is a chip. This is a shear plane. This is a shear plane, right? You agree? This is a shear plane. Chip here will be sheared. The material here will be sheared, and here chip separated. Will be separated. So you can see that this is a shear plane. This is a shear plane actually. This is a shear plane. Can you see that? This is a chip. This is a chip. This is a shear plane. This is the width of the workpiece. This is the width. Width is here, which is this line, right? So this is the width, which is the depth of cut. Width here. This is the depth of cut. Width or depth of cut. This is the TO, uncut chip thickness, or millimeter per revolution, because Listen to me carefully, guys. This is the TO. TO is the uncut chip thickness, or millimeter per revolution, because the tool will cut this one in one revolution, and then next chip shift to cut another TO in next revolution, and another TO in next. So TO here is the uncut chip thickness, or it is the tool feed rate. Why? Because tool feed in this direction. You agree with me? Tool feed in this direction. Tool move in this direction. What is the tool move in this direction? Tool move in this direction, TO. TO per revolution. TO in one revolution, another TO in the second revolution, another TO in another revolution. So TO is a millimeter per revolution. So TO here equal to, can you see that? TO is a millimeter per revolution. This is the feed. TO is the uncut chip thickness, which is equal to millimeter per revolution. And this width, the W here is the width of cut, which is also depth of cut. Initially, tool penetrate to get the depth of cut or width of cut, W or depth of cut. So this width of cut or depth of cut, this is a millimeter per revolution, TO or millimeter per revolution. Anyway, then chip will be removed, and this is a shear plane. Shear plane equal to what? What is the shear area? What is the shear area? Shear area equal to AS. AS is the shear area. This is the area AS equal to what? Equal to W multiplied by TS. W multiplied by TS. And this TS can be obtained as TO divided by sine phi, or TO equal to TS sine phi. TO equal to TS sine phi, then TS equal to TO divided by sine phi, then AS shear area equal to W TS or TO divided by sine phi. This is the shear area. This is the shear area. So this is actually is the shear area here and here. This is a shear area. So AS or shear area equal to W or depth of cut multiplied by TO uncut chip thickness divided by sine phi, which is a shear plane angle. This is the shear area. Shear area, when you come to the shear area, you can see that here we have in the shear area, we have shear force. Shear area, we have here shear force. This is a shear force applied here. This is Fs. This is the whatever we call Fs. Fs shear force applied here. And we have also normal force applied here. This is the Fn. This is the Fn. This is the shear area. In the shear area here we have Fs and we have normal Fn. The Fs and Fn applied in the shear plane. Fs and Fn applied in the shear plane. Then the shear stress here equal to Fs divided by As, or Fs here equal to shear stress multiplied by As, the area of the shear. Then tau or S, they give it sign tau or S. Tau or S is the shear stress equal to Fs divided by As. Then Fs equal divided by As. As equal to WTO sine phi. Then WTO sine phi. Then shear stress equal to Fs sine phi divided by WTO. Right. So even shear force we cannot measure, but we can calculate from the shear stress of the material. If we know the shear stress of the material, for example, if you're cutting steel and you know the shear stress of the steel, you multiply by the shear area, then shear stress multiplied by shear area, then shear force can be obtained. Probably we don't measure the FC and FT, Probably we can just get Fs from the equation here by as a function of shear stress or normal stress, because Fn apply normally, then normal stress equal to Fn divided by also by As. Then Fn here, as you can see, Fn divided by As equal to normal stress. Then if you know the normal stress, you apply As to get Fn. Then normal stress equal to Fn sine phi divided by WTO. This is the shear stress. This is the normal stress. If we know the shear stress and normal stress of the material, we can obtain Fs and Fn. And if we know Fs and Fn, we can obtain the other forces as a function of Fs and Fn. For example, this is the equation, the previous equation, Fc equal to Fs cosine beta minus alpha divided by cosine phi plus beta minus alpha. This one is the Fs value. This is the Fs value. You can apply here Fs equal to what? Fs equal to SWTO SWTO divided by sine phi. This is we put the Fs value here. Then you can get directly Fc as a function of shear stress. So STOW divided by sine phi. This is the Fs value. If I don't know the Fc, I would like to know the Fc, and I don't know the value of Fc, but I know the shear stress, then you can apply in the equation directly here. Then you can obtain the Fc as a function of shear stress and angle. Then STOW cosine beta minus alpha divided by sine phi cosine phi plus beta minus alpha. And Ft also as well can be obtained, and any other value can be obtained as we described earlier. Right? Material removal rate equal to VFD. V is a cutting speed. F is a feed, millimeter per revolution, which is a TO. As we described, feed equal to also TO. Then equal to, we can remove F and say TO, and also D, depth of cut, is equal to width of cut. So a material removal rate equal to VFD or VTOW. Same meaning, same meaning, same meaning. Any question? Any questions? This is really very important. We're going to use this one in the analysis later. You must be familiar with that. You must be able to understand. If you don't understand, then you will have problem later to do analysis in machining. So if you don't understand, please ask me. Right. Then okay. What does the Mershon circle tell us? Mershon circle tell us many shears. Shear angle lead to maximum shear stress. Shear angle lead to maximum shear stress. What will happen here? This is a shear angle. This is a shear angle. This is a shear plane. Shear plane. Here in the shear plane, we said that Fs apply. Here we apply, this is the Fs. You agree with me? This is the Fs. Fs. This is the shear force. Shear force apply here in a shear plane. Normal is apply normally. Right. Fx equal to r cosine phi plus beta minus alpha. Yes, exactly. Yes, exactly. Fs, this one equal to r, Fs, this Fs equal to r cosine phi plus beta minus alpha. They said that in a cutting, when a cutting happens, this material must reach to the maximum. To separate, you must reach to the maximum shear stress. When you reach maximum shear stress, material will be separated. Then shear stress equal to Fs divided by As, which is r cosine phi plus beta minus alpha divided by WTO divided by sine phi. This is the equation. So the shear stress maximum as a cutting shear stress must maximum, means that we need to differentiate to get the maximum shear stress. We need to differentiate the shear stress with respect to the shear angle, d tau divided by d phi, and equal to 0. if you differentiate the shear stress with respect to shear angle and make it equal 0, you get the maximum shear stress. When you do that, you get the equation phi equal to 45 plus alpha divided by 2 minus beta divided by 2. So you can see this equation show relation between phi, alpha, and beta. And this equation is valid unless you do cutting in machining. Because when you do machining, you reach maximum. When you reach maximum, material will be separated. Then you differentiate this one with respect to the phi and make it equal 0. Then you get phi equal to 45 plus alpha divided by 2 minus beta divided by 2. So this is the equation obtained from the maximum shear stress. Then in this case, let's have an example. Using the data, you can obtain actually any angle as a function of other. Using the data from previous example, determine the friction angle and coefficient of friction, mu. Coefficient of friction, which is mu. Previous data said that alpha equal is given 10 degree, phi equal to 45.4 degrees. This is obtained from previous data. Then here you can, as long as you know alpha from previous, this is known, alpha and phi are known. Then you apply here. Then you can get beta. Then beta can be obtained. This is beta. Beta is a friction angle. Then coefficient of friction equal to tan beta equal to this value, right, equal to this value. This is the coefficient of friction can be obtained. Then if you know alpha and phi, you can obtain beta. So using this equation is valid because is in a cutting we reach maximum shear stress, right? Okay, I'll stop here because time is finished. I will stop here. Next time, inshallah, I'm going to continue discussing about the merchant circuit.